So today we're going to change gears and talk about something different from what we've been discussing the last two lectures. So this will be the first out of approximately two lectures on asymptotics. And so the plan for today is first we'll talk about something slightly different. So first we'll discuss the gamma function for two reasons. One is that the gamma function provides a nice simple example for the ideas that we're going to discuss in the rest of the lecture. So it's a simple example where we can construct an asymptotic series without too many complications that occur in more general cases. So that's one reason we'll discuss the gamma function. And the second reason is that there is a particularly important application of the gamma function, namely to dimensional regularization, which we'll go through the math behind dimensional regularization in tutorial this afternoon. So that's the two reasons we're discussing the gamma function, even though it's not quite directly related to the rest of what we're going to discuss. And then I'll tell you more precisely what I mean by an asymptotic series. So an asymptotic series is different from the convergent series you're used to. Asymptotic series in general don't converge. Nevertheless, they do tell us something about the function that they're asymptotic to. They tell us about the behavior in a limit where a parameter approaches a certain value. And I'll be more precise later in the lecture what I mean by an asymptotic series. And then so there are many ways to construct asymptotic series. In physics, the most important one is there's a method for approximating integrals by asymptotic series, and we'll illustrate that method applied to the gamma function to derive Stirling's approximation. And the method we'll use in this simple case we'll generalize tomorrow and generalize further in the quantum field theory courses. So this technique for approximating integrals will come up over and over again in the path or functional integral formulation of quantum field theory. So we're going to gradually build up to a more realistic case, but first starting with the simplest case, generalizing it tomorrow, generalizing further in QFT courses. So that's where we're going today. So let's start with the gamma function, which is defined by an integral. So it's the integral from 0 to infinity of t to the z minus 1, e to the minus t t. And well, this integral converges for large t, regardless of the value of z. E to the minus t goes to 0 sufficiently quickly that there's we don't need to worry about the convergence of this integral at the upper limit of integration. But at the lower limit of integration, there is a reason to be concerned. If z is too negative, or in the case that z is real, if in particular if z is less than 0, then near 0 the integrand will look like t to a power that's less than -1, which is not an integrable. It's not integrable, so this integral won't converge if z is less than 0. And more generally, if we allow z to be a complex number, which will be a case we'll be interested in, the same argument works. So this integral will converge as long as the real part of z is positive. So this is a definition for the gamma function on half of the complex plane. Okay. And well, we want to do better than that. We want to define z on the entire gamma of z on the entire complex plane. And to do that, well, so we can note that the gamma function it's supposed to be a generalization of the factorial. Function. So the factorial is defined for integer arguments. Gamma of z so far is defined on half of the complex plane, so it allows a more general argument. The factorial is basically defined recursively, so we can define n factorial as being n times n minus 1 factorial. That's a so-called functional relation that relates the factorial function with one input to the factorial function with another input. And if gamma of z is going to be a generalization, then it should satisfy a similar sort of functional relation. And we can see that just by playing around with this integrand. So in particular, we take the derivative of t to the z e to the minus t. What we get is z e t to the z minus 1, e to the minus t minus t z e to the minus t. And we can then integrate this from 0 to infinity. Both of the terms over here will be gammas. And if we integrate this left-hand side, we just get two boundary terms. So we'll get t to the z e to the minus t, evaluated at 0 infinity. And here we'll get gamma of z times gamma of z minus gamma of z plus 1. So just integrated this equation from 0 to infinity. And, well, these boundary terms, so at 0, t to the z is 0, assuming the real part of z is positive, and e to the minus t is 1, so we just get 0. And at infinity, the e to the minus t wins, and we again get 0. So we get 0 is z gamma of z minus gamma of z plus 1. Or z gamma of z equals gamma of z plus 1, which should be compared to n times n minus 1 factorial is n factorial. So it's the same kind of relation we had before. So this is the so-called functional relation. And we derived it assuming the real part of z is positive. But we can impose it on the entire complex plane. And if we do that, it gives us a generalization of the factorial that's defined on the entire complex plane. Because so we know if here we've got the real part of z, and we have the imaginary part of z. The integral is defined over here. And if we're interested in some gamma of z over here, we can use the functional relation to relate it to gamma of z plus 1. And if that still has negative real part, we can do it again. And maybe the second time, gamma of z plus 2 can be defined by an integral. So just by repeatedly using this functional relation, we can define gamma on the entire complex plane. So this is, in this way, we can analytically continue the gamma function. Yes?
Shown through this diagram, I don't get that.
So this diagram shows us how we can use the functional equation to make sense of gamma of z when the real part of z is negative. So suppose if gamma of z has negative real part, this integral doesn't converge. So we can't use this integral directly to define gamma of z for the real part of z is negative. But this equation lets us relate gamma of z to gamma of z plus 1. So we can just repeatedly use that to relate gamma of z with negative real z to some gamma of z with positive real part.
If the real part of z is negative, does this method work?
If
the real part of z is a negative integer,
yes,
does this method work?
this derivation doesn't work. This step fails. So this, we can derive this on this half of the complex plane, and we can just impose it. So it's an extra input.
But if the real part of z is a negative integer, then if you sum 1 to it, you're going to get to 0. Or if you sum an integer to it.
Yes.
So we still have a problem in the strips given by real part of z equals negative integer, don't we?
There is a problem there. I'll get to that in a minute. Yes. Okay. Yeah. So as Rick was pointing out, there are. So this works almost everywhere over here. There are potentially isolated points where this fails, which I'll address in a minute.
And is it going to be that it fails that like the function is not going to be uniformly continuous, so we're not going to be able to cover those points? Or?
What we're going to see in a minute is there's going to be some poles. Okay. So this. The other thing I want to point out before I get to the point that's been raised about points where this fails is, well, gamma is supposed to be a generalization of the factorial. So let's try to make that identification. So gamma of 1 is 1. Just if we plug in z equals 1, this term goes away. It's an easy integral to evaluate. It just gives us 1. And so we know that gamma of z plus 1 is z times gamma of z. So together with this initial condition and the functional relation tells us that for integers, gamma of n plus 1 is n factorial for positive integer n, or non-negative integer n. So there's this unfortunate mismatch and the arguments. They are related. And yeah, so that to generalize this procedure, so we can define gamma of z for negative z as gamma of z plus n over z plus 1 up to z plus n minus 1, where the real part of z plus n is positive. So we just iterate, use this functional relation n times. We can relate gamma of z for negative real part to some gamma function with a positive real part of the argument. And so the issue that was brought up before about isolated points where this fails is related to this equation here. Because if one of these factors is 0, then that's when this can fail. So if, in particular, if we look at gamma of z at negative integer points, then one of these factors on the bottom will be 0, and that means there will be a pull at the negative integers. And so this tells us that there are poles at the negative integers. And for dimensional regularization, which we'll go through in tutorial this afternoon, it will be useful to determine the residue at these poles. So we can do that, again, just by using this formula. So let's take z to be equal to 1 minus n plus epsilon. Then, using this formula, gamma of z is gamma of 1 plus epsilon. And for here, we've got epsilon minus n plus 1 as this first factor, epsilon minus n plus 2, all the way up to epsilon minus 1 and epsilon. And if we take epsilon to 0, this just gives us gamma of 1, which is 1. And down in the denominator, we've got all of these factors are negative. So we have n plus 1 negative signs. And we've got here an n minus 1. This is an n minus 1, n minus 2, down to 1. So n minus 1 factorial. So it's approximately this as epsilon goes to 0. So that tells us that the residue at z equals minus n is, so here everything is shifted by 1. I shifted by 1 just so I could get a gamma of 1 in the numerator. We unshift things, we get residue of minus 1 to the n over n factorial. And this result will be useful in tutorial this afternoon. And it can be shown that, I won't go through it now, but there gamma of z has no other poles and no zeros. So if we sketch a plot of gamma of x versus x for x real, it'll look something like there's a pole at 0, goes to infinity over here, and then it switches sign. Pole, something like this. Okay. So the takeaway points are there are isolated poles, these residues, and we can define gamma on the entire complex plane via a combination of this integral and this functional equation. So we'll come back to this twice. So at the end of the lecture, we'll illustrate our techniques by approximating this integral for large z, and we'll also come back to it in tutorial for dimensional regularization. Okay, so let's move on to our main topic for today, which is asymptotics. And the reason we're interested in this is that it's very common in physics that we're interested in studying a system that we can't study exactly as a function of all of its parameters, but we know those parameters are very large or more commonly very small. So asymptotic series are and asymptotics in general are a good way to study the behavior of some function when some of its parameters are large or small. So you want to do an expansion in a large or small parameter. In general, what we get is an asymptotic series. If we're lucky, we'll get a convergent series, but that turns out to be fairly rare, at least in quantum field theory, that we can actually get a convergent series expansion. So in general, if we're interested in the behavior of a system, say our coupling constant becomes small, the best we can do is find an asymptotic series. And one of the main approximation techniques we'll use in quantum field theory is called the saddle point approximation. We'll discuss tomorrow and in a special case today. And the saddle point approximation does not, in general, give a convergent series. It gives an asymptotic series. So to illustrate why that's the case, let's look at a toy model. This will be a simple version of a quantum field theory that we'll study later in the year. So you can think of this as a zero-dimensional path integral, which just becomes an ordinary integral. So we've got some function z of lambda, which will be e to the minus integral of e to the minus x squared minus lambda x to the fourth dx. Okay. So this is a simplified version of the kind of integrals we're going to want to approximate in quantum field theory. So if lambda is 0, this is an integral we can do exactly. It's just a Gaussian integral. But if lambda is finite, Well, it turns out in this simple case we can still do it exactly, but that technique fails for the realistic case. So we'll just ignore the fact that we can actually evaluate this exactly for finite lambda, and approach it in the same way that we would approach the quantum field theory problem. So if we want to make further progress, one thing we can do is we can expand e to the minus lambda x to the fourth. So that has a convergent series expansion. You can write it just as minus 1 to the n, lambda to the n, x to the 4n over n factorial. So this is just the series expansion for e to the minus lambda x to the fourth. And if we want to make further progress, we have to do something a bit sketchy, which is swap the sum and the integral. There's really nothing else we can do to make any further progress. So let's do the only thing we can. It's not clear a priori whether that's justified or allowed or what we'll get if we do it, but let's proceed anyways. Swap the sum and the integral. And then what we get is the integral of e to the minus x squared minus lambda to the n x to the 4n over n factorial dx. So each of these integrals, each of the terms in this series is an integral of e to the minus x squared times monomial in x. Those are one generalization of Gaussian integrals. So Gaussian integrals are very important in quantum field theory. So basically for this reason, because this is one of the main techniques we'll be using to approximate many of the quantities we're interested in quantum field theory in the path integral formulation. So, and something else we'll just go over in tutorial is some generalizations of the ordinary Gaussian integral. This is one of the simpler ones. We'll discuss some others. So one way we can do this is using techniques in tutorial. Another way we can evaluate each of these integrals is by making a change of variables. So if we let u equals x squared, then this e to the minus x just becomes e to the minus u, and then we've got some power in front, so it looks like a gamma integral. So what we get here is e to the minus u minus lambda to the n, u to the 2n over n factorial du we get over, from the change of variables, we get a half and a u to the minus a half. And we can also, the integral is even, so we can change the limits to be from 0 to infinity and get an extra factor of 2. So I just did the change of variables and noted the integral is even. And each of these integrals is a gamma integral. So what we get is that z of lambda, assuming this step is OK, is the sum from n equals 0 to infinity minus lambda to the n for n factorial gamma of 2n plus a half. Okay. So, well, we could evaluate this integral using this technique, which is the one we're going to use in quantum field theory repeatedly. There's only one problem, and that's that gamma of 2n plus a half is, well, for n large, we can say this is about 2n factorial, which is certainly greater than n factorial squared. There's an n factorial in the second half, or the product of 1 up to n, and then we've got a product of n plus 1 up to 2n. Each of those terms is bigger than the corresponding term in n factorial, so this is certainly much bigger than n factorial squared. So the term, the coefficients grow factorially, which means this series diverges. Okay, so we've got a series expansion that diverges. Well, we're not going to let the divergence of the series stop us. This is a very useful technique. So swapping the sum and the integral is what is the origin of this divergence. And simply the fact that we get infinity shouldn't stop us. We can make sense of a result, and it's actually a very useful result. And the types of results we're going to get in quantum field theory are, in general, all going to be divergent asymptotic series. Nevertheless, they contain useful physical information about the quantum field theories we're going to study. Okay, so this is our first example of an asymptotic series, and so this shouldn't be an equal sign. Not equal to. It's the correct statement is that this is asymptotic to as lambda goes to 0, and I'll explain what that means in a moment. Still a useful relation, even though we no longer have an equality.
Can we say what fails in swapping that sum and that integral? Because the exponential converges uniformly everywhere. So, and it's well known that uniformly convergent series can be exchanged with integration. I don't see where. I mean, does that integral converge to begin with?
This integral converges. This converges to e to the minus lambda x to the 4th. In general, if we have a convergent series where it's not necessarily true for every convergent series that you can change the order in which you add together the terms. That in general changes the sum of the series. And so if we're swapping the sum and the integral, we're essentially changing the order in which we're adding the terms together. And in general, that changes the value of the sum. If you put sufficient conditions on how quickly it converges and what the growth of the terms, then there are some cases where you can switch it, but in general, it'll change the value.
How do we know which cases we can switch it in? Because like this was clearly not a good idea, switching it up.
It was a great idea, actually. This is our.
we didn't get an answer.
This is
solution doesn't converge, so like
doesn't converge. It's still a useful result, and basically to make any progress in studying most quantum field theories, we're going to have to do this. This series does contain information about this original quantity we're interested in. And
switching up the order asymptotically makes the latter expression equal to the first one. Is that what you're saying?
I'm not saying that these two things are equal. I'll explain what asymptotic series means first, and then perhaps I can come back to your question, or if I don't address it, ask again or ask me after lecture.
So is there various conversions of lambda for which they're missing? Series conversions?
For lambda equals 0, it converges. It has a 0 radius of convergence. Okay. Yes.
Why do we write that as like asymptotic, like with lambda going to 0? Like what is? Because I thought when lambda equals 0, you like regain the Gaussian distribution. So what is it?
That's the next thing I was going to talk about. So ask again if it's not clear in a few minutes. Okay. So what? Addressing Elizabeth's question, what does that symbol mean? So let me give you a few definitions. So our first definition, we can say that a function f is much less than another function g. This means so this, as x approaches x naught, means that the limit as x goes to x naught of f over g is 0. So this is related to what it means to be asymptotic too, but it's a useful building block. So this is a slightly different use of much less than you may be used to. So some cases where it behaves just like you'd expect. So for example, x is much less than 1 over x as x goes to 0. We take this ratio, we get x squared, which goes to 0 as x goes to 0, and well, this goes to 0, that blows up, so that makes sense. There's also some weird relations we can write down that are correct with this definition. For example, x squared, which for real x is always positive, is much less than, as x goes to 0, -1. So x squared is both much less than -1 and greater than -1. It's weird, but that's the way definition works. Okay. So our second definition is two functions are asymptotic. Asymptotic too. If f minus g is much less than g, or equivalently, the limit as x goes to x naught of f of x over g of x is 1. So some examples. Cosine of x as x goes to pi is equal to -1. So cosine of x just approaches -1 as x goes to pi. That's exactly what you'd expect. It's another example. So x squared goes to 0 as x goes to 0. So we might want to write x squared is asymptotic to 0 as x goes to 0. But let's check and see if that makes sense. So one way to, one of the two equivalent conditions for two functions to be asymptotic is that the limit as x goes to x naught of f over g should be 1. The limit of x squared over 0 is not 1. It is not defined. So this doesn't work. So asymptotic 2 is not just a statement about the limit of the two functions as they approach the point, but it contains information about how quickly the functions approach each other as x goes to x naught. So x squared is approaching 0 at a different rate from 0 as x goes to 0. So not asymptotic as functions. And similarly, x squared and x, even though they're both approaching 0, they approach 0 at different rates as x goes to 0, so that they're not asymptotic either. So this tells us about how quickly the functions are approaching each other. So if they're approaching each other quickly, then this difference will be much less than one of the functions. Okay. And the most important definition, the one we'll be mostly interested in, is asymptotic series, which is basically an infinite set of asymptotic relations like this. So a function has an asymptotic series as x goes to x naught. Of this form. This is so this means that y minus the partial sum from n equals 0 to big N of an x minus x naught is much less than x minus x naught to the n. So this is partial sum, and this should hold for all n. So the difference between the function and the partial sum of its asymptotic series has to be much less than x to the n. That's what it means for this to be an asymptotic series, and that's what we found before. I'm not going to prove it. General proving things are asymptotic series will be more work than we can usually do in many, but in general, the techniques I'm going to describe will give us asymptotic series. So that's the interpretation of our result before. So this doesn't, the asymptotic series tells us about how about how quickly z of lambda how z of lambda depends on lambda near lambda equals 0. So that's the type of information we get from the asymptotic series. And that's the information we're guaranteed to get. In many cases, we can actually get more information, and there are situations where the partial sums do tell us something about the original function, and I'll say more about that next week. But all we're guaranteed is that the asymptotic series contains information about how the function depends on x or lambda as we approach the limit.
In the first sum over there, it should be the exponent should be n.
Yes, thank you. So a few comments about asymptotic series. So the first comment is that convergent series are better approximations as we take more terms. That is not necessarily true for an asymptotic series. There's, and in fact, since most asymptotic series are divergent series, that suggests that the typical case is that an asymptotic series, if the partial sum is a good approximation to the original function, that will only be true up to a certain number of terms. If we take too many terms, our approximation will get worse and worse, because this side, the series will generally diverge. The function we're finding an asymptotic series for usually doesn't. So what asymptotic series get better, are better approximations as x goes to x naught with a fixed number of terms. And taking too many terms usually makes the approximation worse. Okay, so
sorry, is this taking too many what?
too many terms. Another important comment is that if f of lambda is asymptotic as lambda goes to 0 to some series, then so is f of lambda plus e to the minus lambda squared, 1 over lambda squared. And that's because e to the minus 1 over lambda squared is much less than lambda to the n for any n as lambda goes to 0.
So for the higher power lambda, for example, 1 over lambda to the fourth power, so is it also the...
That would also be an example. So we could, there are other functions we could put over here that it would be much less than lambda to the n. This is just an example. But this observation tells us something important. Namely that if we're, since our main technique in quantum field theory for approximating the quantities of interest involves finding asymptotic series, we're missing something. There's no way we can recover any information if the quantity we're interested in contains a term that's like e to the minus 1 over lambda squared. We'll never see that if we're finding an asymptotic series. So there's information that's missing in an asymptotic series. Another way of stating the same thing is if we, there's some quantity of interest, f of lambda. Well, there's a unique procedure for finding the asymptotic series. So going this way is unique, but going backwards is not unique. So if all we have is the asymptotic series, there's information we're missing about the quantity of interest. And well, yeah, so one caveat about this non-uniqueness. So if we don't know anything else about this function, then this is non-unique. If we have some extra information about this function, sometimes we can go backwards. And the types of terms we're missing are terms like e to the minus 1 over lambda squared. And those terms are relevant for physics. So what we're missing, so this is an example of a non-perturbative term. And terms exactly like that are relevant for physics in some cases. So in one example, is tunneling or vacuum decay. So tunneling through a barrier in quantum mechanics. If you tried to use techniques I'm going to describe about finding asymptotic series, tunneling will be invisible. So while the techniques I'm going to describe for finding asymptotic series are important, they're not the whole story. We're missing tunneling, vacuum decay, U1 axial current non-conservation in QCD. There's a number of examples where important physics is missed by these techniques. And we'll discuss ways to extract this non-perturbative physics in a number of the elective courses. But for the first part of the year, for the core courses, we'll be focusing on the perturbative physics, but just keep in the back of your mind that we are missing some of the physics, these techniques. And another comment is that in the case where we're dealing with an asymptotic relation in the complex plane, an asymptotic relation like this is generally only valid in some wedge where, say, the argument of z minus z naught is between two constants a and b. And that's because well, e to the non-perturbative function we looked at before, e to the minus 1 over lambda squared, goes to 0 as lambda goes to 0 for lambda real. But e to the minus 1 over lambda squared, lambda goes to 0, or diverges as lambda goes to 0 if lambda is imaginary. So this non-perturbative term could, in the case where we have a complex parameter, could be completely unimportant if we approach the limit point we're interested in from some direction, but could be the most important thing from other directions. So I'll have more to say about this tomorrow. Is there a question?
I have a question.
Yes.
I don't get what in which whatever you wrote after that.
Okay, so this is saying that, so suppose we're interested in an asymptotic series. Here's the real part of z, here's the imaginary part of z. You want to have an asymptotic relation or asymptotic series around some point z naught. And so what this is saying is that generally there's some wedge in the complex plane where the asymptotic relation will be valid if we approach the point along some curve inside this wedge. So a curve that approaches z naught from inside this wedge. So that the relation f z versus z naught as f of z is asymptotic. Z might be valid for a curve that approaches from this direction, but will fail if it approaches from some other direction. That's what that's saying. So the argument of z is telling us about which angle we're approaching the limit point.
So is it the angle only relevant with the point z, not with the function?
Well, so an asymptotic series is only tells us about what's going on in an infinitesimal neighborhood.
Yeah, I'm talking about the angle. So is the angle only given a point z0? Can we specify the angle without knowing which function we are studying.
So in general, how big the wedge is,
Yeah.
that will depend on the particular functions.
Okay.
So we'd have to analyze the particular problem in order to determine what A and B are. In general, there will be some A and B, but without knowing anything else about the problem, we can't say what they are. Okay. So the most useful way of constructing asymptotic series, at least for physicists, is a technique that gives you an asymptotic series for an integral. So for the example we're going to look at today is an approximation to the gamma function, which I gave you an integral representation of the gamma function at the beginning of lecture, and we'll look at a more general way to apply this technique tomorrow. It's not the only way we can construct asymptotic series, but it's by far the most useful way for physics. That's what we'll focus on. In the tutorial, we might briefly discuss another way, but by far the most useful way of constructing asymptotic series is assuming that whatever we want to approximate is written as an integral to begin with. So we are going to approximate gamma of, let's say, x plus 1, which is, if x is an integer, x factorial. For large x, large real x. And chose this example not because we particularly care about this expression, but just because the technique itself is important. And it's a simple example where we can illustrate the technique that we're going to use over and over again throughout the year. Okay, so using our expression from the beginning of lecture, the integral expression for gamma is e to the minus t, t to the x, dt. And the key observation we need to make in order to derive an asymptotic series for this result is that if we look at the integrand, e to the minus t, t to the x, as a function of t, the integrand for t small goes to 0 very rapidly, particularly because we're interested in large x. So near for t small, this function rapidly goes to 0. It also goes to 0 very rapidly for t large. The exponential goes too quickly. It goes to 0 very quickly. So the function should look like something like this, and it should be peaked somewhere in the middle. And this peak should get narrower and narrower as we take x to infinity, because this goes to 0 more and more rapidly over here. So this is sharply peaked. As x goes to infinity. So if we want to approximate this integral, the natural way to try to approximate this integral is to look at this rough sketch of the integrand and say that most of the contribution to the integral will come up from some region. A small region near the max of e to the minus t, t to the x provides a dominant contribution. Okay. And, well, we could just find the max directly by looking at this, but we're going to manipulate the integrand a little bit to put it in a form that will be match the types of integrals we'll see in quantum field theory a bit more closely. So we can write this integrand as e to the minus x times, sorry, I'm going to do a change of variables first. I'm going to do a change of variables, t equals wx. Write this as x to the x plus 1, integral from 0 to infinity, e to the minus x, w minus log w, dw. And this integral is of the form e to the minus x, f of w. And this is the type of integrands that we'll encounter in quantum field theory in the simplest case, where our parameter is some is multiplying everything else in the exponent. So that's the reason I did this change of variables, and just to make it match more closely with the at least the simplest integrals will approximate QFT. So in this form, what we care about are, when f is minimized, then this integrand is maximized. And, well, so we need to find the minima. F prime of w is 1 minus 1 over w. So this is 0 when f equals 1. So if we approximate f, it's Taylor series around w equals 1. Then we'll contain, we'll get most of the information about what the function is doing near where the integrand is highly peaked. Yes.
Why can you say t equals wx? Because isn't that imposing a relationship between t and x that we don't necessarily know?
Well, we're interested in approximating this. We're interested in this for large values of x, but we can think about just some large fixed value of x. So then x is, thinking about it that way, x is a constant, and we're just changing our integration variable from e to w. It's a change of variables we're allowed to do. The reason I did that is because I wanted the integrand to look like this, to have a x multiplying everything. Did that address your concern?
Yeah.
Okay. Okay, so near w equals 1, the integrand, or the function f, the exponent of the integrand, looks like 1 plus a half w minus 1 squared. We could include higher order terms if we wanted. For now, we won't. I'll briefly comment on what would change if we did near the end. And so using this approximation for f, what we get is gamma of x plus 1 is x to the x plus 1 e to the minus x. The first term just is a constant that factors out of our integral. Integral e to the minus x over 2 w minus 1 squared plus dot dot dot. So the nice feature is that this quadratic term gives us a Gaussian integral. And those are integrals we know how to do. So this is a Gaussian integral. At least if we ignore the dot dot dot. And so that's an integral we can do. Get x to the x plus 1 e to the minus x root 2 pi over x. And so that's the first term. We can include more terms. And just comment briefly a bit about how we do that. So if we included a next term here, a cubic term, that would give us a very difficult integral to do. Doing a integral of e to the minus some polynomial in general is hard to do if the polynomial is of degree higher than 2. But what we can do is basically the same thing we did before. So if we have a e to the, we wanted to include more terms. We have a e to the minus x over 2 w minus 1 squared plus, say, c3, some constant, which we could compute if we wanted to, and some higher constants. What we could do is just basically the same thing we did before. Our very first example of that toy model at the top board on the left. So we could Taylor expand all of these terms. And what we would get would be, we'd still want to keep the quadratic term. And then we get this multiplied by a series outside of the exponent. And we'd have some other constants here, which we could compute these constants, C3, C4, equivalent, and relate them to A1 and A2 if we wanted to. We'll do that later, but for now, I'll just note that we could. And these are integrals that we can do. So we saw one way to do it earlier in the lecture where we could relate them to gamma integrals. We'll see some other ways to evaluate these integrals in tutorial, and yet other ways later in the quantum field theory courses. So we can include corrections systematically to this result. And if we did that, what we would get is So what we would get is an asymptotic series, not for gamma of x directly, because we have these extra factors out front. What we would get is an asymptotic series for gamma divided by some extraneous factors, 2 pi x to the x plus a half e to the minus x. This would be asymptotic to x goes to infinity. 1, so that's the term we computed. Be the first term in the asymptotic series. If we went to higher terms, we get 1 over 12x. So this is an asymptotic series, not in x, but in 1 over x. Using the same definition, where we can just replace x minus x naught to the n with x minus x naught to the minus n. This is our asymptotic series result. And so this is the simplest possible example. We'll look at more involved examples, but I just want to summarize the key steps of what we did, because the key steps, although each of the steps will get slightly more involved when we look at more realistic examples, or examples that will be more directly analogous to the ones we'll look at in quantum field theory, the steps are basically going to be the same. So first what we did is we looked at the integrand and saw that in the limit we were interested in, it became highly peaked. So, so let's summarize the steps. Identify region where the integrand is highly peaked. Then what we did is we turned the integrand into a Gaussian integral. We approximated the integrand with a Gaussian integral near the peak. And we evaluated. So each of these steps will get slightly more involved, but just want you to have an idea of the general picture of what we're going to do, both in lecture tomorrow and in tutorial tomorrow, as well as in the quantum field theory courses. So each of these steps will be somewhat more involved, but it's generally the same thing. The reason we approximate with Gaussian integrals is because these are basically the only types of integrals we can evaluate. There's one step I skipped over here. I just want to point out that this is almost a Gaussian integral. Gaussian integral would have a limit from limits of integration from minus infinity to infinity. Our original integral is from 0 to infinity. But our original integral is highly peaked around w equals 1. So we won't change the integral very much if we extend the limits of integration from 0 to infinity to minus infinity to infinity. So this is Gaussian after extending the limits of integration. Okay. That's so this is basically what we're going to be doing tomorrow. So tomorrow we will apply this method two integrals of the form. We've got a complex integral, where we have some function g some integral like this, where this is some complex integral and our parameter z, which we're taking to be large, might also be complex. So same steps will work in that case. I'll have to take into account a few extra details, but the basic idea is the same as what we just saw. Not tomorrow, next week.